Hello, welcome to Equity Education, the chemistry version, and today we're going to be looking at alkanes. Right, so this is organic, and we'll go ahead and get started. So I'll let you to open up your booklets. Okay, so we'll start with the general formula. So the general formula for an alkane is CnH2n plus 2. And that means that if I had an alkane with 3 carbons, which would be my N, I would have times 2N for my number of hydrogens plus 2. So 2 times 3 is 6, plus 2 is 8. Okay, so hydrocarbon, this is a definition, a molecule that contains carbon and hydrogen. I'm just going to change colour now because this is important. You have to write only, so contains carbon and hydrogen only. A saturated hydrocarbon or saturated hydrocarbons, a molecule that contains, again we've got this word only, single covalent bonds. So in other words, there's no double bonds. Okay, alkanes and cycloalkanes. So have the suffix. So suffix means the ending. So they have the ending ane. E.g. So I could write the structural formula CH2, CH3, and we would call this 1, 2, 3 carbon. So we know it's pro. We know the ending's ane, so propane. This is a skeletal formula, so 1, 2, 3, 4. So I know it's bute, my longest carbon chain. I know it ends in ane because it's an alkane, and I've got a branch coming off here, and it's got 1 carbon on, so it must be 2-methyl butane. Let's write that slightly clearer. So 2-methyl butane. Okay, and this over here is another skeletal formula. It has 1, 2, 3, 4, 5, 6 carbons, but they're in a ring. So that means we're going to call it cyclohex for 6 and ane because it's a alkane. Okay, so moving on. So the shape of an alkane. So an alkane has a tetrahedral shape with a bond angle of 109.5 degrees. And if I was going to draw this, I'm just going to draw the simplest alkane. So I'll draw methane. It would look like this. So you may notice I've drawn this wedge and I've drawn this dash here, and this just means that one's going into the board and one's going out of the board. So if you can see that, looks like that. Yeah, so it's a 3D structure. So my bond angle here is 109.5, and we only measure bond angles between bonded pairs here. Don't worry too much about that. Probably come on to bond angles a bit later. So 109.5 degrees. Okay, so the covalent bonds, these represent the covalent bonds, are sigma bonds. This is my symbol for sigma. These form by the overlap of atomic orbitals. I don't want to go into too much detail because you don't really need to know. Okay, the reactivity of alkanes. So alkanes are generally considered unreactive because of the non-polar bonds, or really we should put non-polar nature of the molecule. Okay, so there is little difference in electronegativity between carbon and hydrogen, which means it is less prone to nucleophilic or electrophilic attack. Again, I don't want to go into too much detail here because it will start to become more obvious as we continue through the course. Okay, so the strength of the carbon-carbon and carbon-hydrogen is relatively strong. Therefore, they require a lot of energy to break. So these two reasons here, so because it's not a polar molecule and there are no real polar bonds, there is little difference in electronegativity between the carbon and hydrogen, so we say it's a non-polar molecule. It's not prone to nucleophilic or electrophilic attack, and also because of the strength of the carbon and carbon-hydrogen bonds, it's quite like a lot of energy to break them up, so they're generally considered unreactive. Okay, so moving on. The physical properties of alkanes. So, as carbon chain length increases, so does the boiling point. This is because the carbon chain length increases and therefore there are more electrons as the molecule gets bigger. These two factors mean there is an increase in the strength of the intermolecular forces between the molecules, and we can see this on this graph here. So as the carbon chain length increases, in general the boiling point is increasing as well, and this is because of these intermolecular forces. Again, if you're unfamiliar with all these words, if you continue watching the videos, because this is just an introduction to alkanes, it should start to make a bit more sense. Okay, so volatility. So volatility is the ease at which a liquid turns to a gas. So volatility decreases as the carbon chain increases for the same reason as the boiling point. Okay, so the boiling point increases because we have more intermolecular forces. Must mean we need more energy to break them forces, and that must mean that the volatility, so when it goes from a liquid to a gas, must decrease because it needs more energy to turn an alkane from a liquid to a gas. So same reason. Okay, so branched chain alkanes. So we're still talking about physical properties and boiling points. So branched chain alkane, so we have 3 molecules here and they're all the same. So 1, 2, 3, 4, 5, 6. 5, 6. So this would be hexane. Is here 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. I should have done another one. Let's do another one here. So 1, 2, 3, 4, 5, 6. Okay, so this would be 2 methyl pentane. Okay, so I'd like you to have a go at working out the molecular formula of these. I'll give you a minute. Okay, I'm sure you've used the general formula to work this out. So my general formula is CnH2n plus 2. I have 1, 2, 3, 4, 5, 6. So 6H12 plus 2 is C6H14. 1, 2, 3, 4, 5, 6, which means this is exactly the same as my molecular form. It's exactly the same molecular formula. Okay, so the reason why I got you to do that is because of this down here. So the more branches an alkane has, the lower the boiling point. This is because the molecules cannot get as close to each other, so have less points of contact. This decreases, I haven't left much space there, the strength of the intermolecular forces. Okay, so between here, for example, we could say lots of points of contact, but in my branch chain alkane there may be less points of contact. And remember, when we're talking about boiling points of alkanes, we're talking about breaking these intermolecular forces. So not the actual molecule, it's the forces between the molecules. So if I have more points of contact, I increase the intermolecular forces, so this would have a higher boiling point. Less points of contact, therefore less intermolecular forces, therefore a decrease in boiling point. And just another point on boiling point, when I say boiling point, the exact same reasoning that I'm using would be for melting point as well. Okay, so moving on. So where do hydrocarbons come from? Okay, so hydrocarbons, where do they come from? Just bear with me a second. Okay, I'm back. Wasn't sure what was going on with my formatting on my page there. Okay, so where do hydrocarbons come from? So, hydrocarbons come from crude oil. And crude oil is a finite resource. A finite resource is non-renewable. Okay, crude oil is a mixture of complex hydrocarbons, and we need to separate these hydrocarbons so they can be used. This is done by something called fractional distillation. And fractional distillation works because the hydrocarbons have different boiling points. So this is the main reason why fractional distillation works, because the different fractions of the hydrocarbons can be separated because they have different boiling points. Okay, so the hydrocarbons are separated into fractions. Fractions are a smaller mixture of hydrocarbons. These can be distilled further to get useful products. Fractional distillation is carried out in a fractional distillation column. And we have a diagram here. Okay, so the main thing to take away from this is that large molecules at the bottom are going to have a high boiling point or a higher boiling point. So if you see here, this is where the hottest part of the fractional distillation column is. This is cool up here. Therefore, the molecules with the higher boiling points, which is the longer hydrocarbons, are going to condense off first. So they turn into a gas, then a liquid, and condense off here. Molecules with a smaller carbon chain length will have a lower boiling point, so they will move all the way through the column and start to condense up here. Okay, alright, so I'm not going to talk that much more about, well, that's it about fractional distillation column and fractional distillation, because it's usually GCSE rather than A-level. Okay, moving on. So, hydrocarbons as fuels. So, hydrocarbons are generally used as fuels using a combustion reaction. So definition, complete combustion is A compound is burnt completely in excess oxygen to produce carbon dioxide and water. Usually we only have to use completely or excess, but I've stuck it both in. E.g., so say I have this, which is ethane. I'm going to react it with oxygen. What am I going to produce? Well, I'm going to produce carbon dioxide and water. So the thing that you'll have to do is probably balance this, yeah? And the easiest thing to do is balance the carbons first. So balance the carbons, so there'll be 2 carbons, 2 CO2s, because 2 carbons over here. Then balance the hydrogens, so H6, so this must be 3H2O. And then go back and balance the oxygens. Because oxygen is on its own, it's very easy to balance. So 2 times 2 is 4, plus 3 is 7, so I must need 3.5 oxygens. Okay, incomplete combustion is a compound is burnt in a limited supply of oxygen to produce carbon monoxide and water. E.g., let's do it with ethane again, and I want you to have a go at doing this, so see if you can do this equation and balance it. Okay, I'm sure you've all done this, so I've got my ethane. Remember, do the carbons first, so 2CO. Remember that we're producing carbon monoxide this time, not carbon dioxide. Still producing 3 moles of water, because I have H6 over here, which means I need 2.5 O2. Okay, so in even more depleted oxygen environments, often carbon and water are the major products. And we'll quickly do this together. So we'll use ethane again. So I'm still reacting with oxygen, but my major product is going to be carbon, which is usually, I'll just write this here, in the form of soot. So that's the black stuff you see if you've got a fire, so a coal or wood burning fire. So we need 2C, 3H2O, so I need to balance my oxygens, so I have 3 oxygens, therefore 1.5 oxygens. Okay, right, so moving on. So making longer hydrocarbons into more useful products. So shorter alkanes and alkenes generally have more demand than longer hydrocarbons. The process by which they are produced is called cracking. So cracking, as we basically just said, is when long chain hydrocarbons are broken down into shorter alkanes and alkenes using a catalyst. Okay, so the catalyst, we've got 2 different types. We could have thermal cracking or catalytic cracking. We'll talk about catalytic cracking. So catalytic cracking uses a catalyst. This catalyst called a zeolite. You don't need to know what they are, but generally they're a mixture of aluminium, silicon and oxygen. Okay, so just remember this name, so zeolite. The alkanes that are produced are used in fuels, and the alkenes are used to make plastics. And we'll do an example. Okay, so I'll pick a long chain hydrocarbon, C30. I'm going to make it an alkane, so C30, 2N60 plus 2, 62, goes to a shorter hydrocarbon, so maybe C14. So this would be my alkane plus an alkene, and I'm going to use C8H8. I want to see if you can figure out what's wrong with this equation, see if you can work out what to do. Okay, as you've probably worked out, it's not balanced, yeah? So 14 plus 8 does definitely not equal 30, therefore we had to put 2 moles of C8H18 here, which would give us 16 carbons here, 14 here, which equals 30. So maybe in the exam you may have to work out the number of moles if you've only got 2 products. Okay, moving on. So we're talking about making longer hydrocarbons into more useful products. Cracking is one method. The next method is isomerization. And this is generally taking a straight chain alkane and turning it into a branched chain alkane. E.g., again I'm going to do a skeletal formula. 1, 2, 3, 4, 5. We'll do it with hexane. So this would be hexane. And I'm going to turn it into 1, 2, 3, 4, 5. This 2-methyl pentane. Okay, so I've taken my straight chain and turned it into a branch chain. So this would be hexane. And this is 2-methyl pentane. The catalyst that is usually used is usually platinum. Okay, so the next process is called reforming, and there are lots of different ways we can reform alkanes, but these I'm just going to give you 2 examples. So first example is when I take a branched chain alkane and turn it into a cycloalkane. E.g., let's take my 2-methyl pentane, and we said we need to turn it into a cycloalkane. So we have 1, 2, 3, 4, 5, 6. So C6 H14. So that I need to turn it into cyclohexane. And I want to see if you can work out what the molecular formula of cyclohexane is, and then see what might be wrong with this equation. Okay, as I'm sure you've worked out, you probably worked out that cyclohexane has the molecular formula of C6H12, which doesn't add up to C6H14. We've got an extra 2 hydrogens. So when we're reforming from a branch to a cyclo, we always produce hydrogen. So branch to cyclo forms hydrogen. Okay, and the catalyst is usually platinum or rhodium. Okay, next process. So again, this is just an example. So an alkane, just any alkane, into an aromatic compound. So an aromatic compound, you may not have heard of this. And this is a compound that involves something called benzene. Okay, and I'm just going to show you the formula of benzene. Benzene looks like this. So it looks like cyclohexane, but has this circle in the middle. You don't really need to know what this circle is, but you need to know the molecular formula is C6H6. So you need to be able to recognize this. Okay, so an example is 1, 2, 3, 4, 5, 6. So I'm going to take my hexane. Whoops, that's definitely not hexane. So I'm going to take my hexane, which has a molecular formula of C6H14, and I'm going to turn it into benzene. Okay, again I want you to see if you can work out what the other product is. Okay, as I told you, that this molecular formula of benzene is C6H6, so we're missing a fair amount of hydrogens. So we're missing 8 hydrogens. So that must mean we're producing hydrogen here, and we must need 4 of them. And the catalyst. So the catalyst is again usually platinum and a mix of aluminium oxide. You may see lots of different catalysts for these types of reactions though. These are generally the most common ones. Okay, so why do we do this? So isomerization and reforming are both done because the products combust much more efficiently than straight chain alkanes. Therefore, they are therefore added to petrol. Okay, so the 3 processes whereby hydrocarbons are produced in more useful products are: first one, cracking; second one, isomerization; and third one, reforming. You may see it with a hyphen, you may not. Okay, so moving on. Again, this is quite a lot of information, not that much chemistry going on, and I'm going to go through it quite quickly. So fossil fuels versus renewable resources. So non-renewable fuel sources. So fossil fuels are non-renewable. Fossil fuels are mainly found in crude oil. And remember, non-renewable means they can't be used again. Problems with fossil fuels. So when we combust them, we increase the CO2 levels in the atmosphere, which leads to global warming. And burning fossil fuels can lead to acid rain, and that's because we have sulfur oxides and nitrous oxides in the fossil fuels which can be released, and this can damage building and aquatic life. So it goes into rivers, acidifies the rivers or the lakes, and can kill the aquatic life within it. Okay, so renewable fuels. So these are resources that can be used again. E.g., and I'm sure you know these: solar, wind, hydroelectric, geothermal, and we'll put one more down because I want to roll waves. There are others, but there we go, we got some examples. So renewable resources are a lot cleaner than fossil fuels and considered less damaging to the environment. Again, I'm just going to state these things because, well, that's it. They're just facts, basically. Biofuels. So biofuels, fuels that are derived are generally fuels that are derived from plant materials, and one of the most common ones is bioethanol. So bioethanol can be produced from crops, for example, growing sugarcane, and we ferment that sugar to turn it into ethanol, and then we can use that ethanol as fuels in cars. Problems with biofuels. So crops that are used to produce biofuels could be used to feed people. So there's a massive debate around all of this. I'm not going to go into it because you're not going to need to know it for your exams or if you're learning the chemistry behind it. Okay, so been through that quite quickly because, to be honest, there isn't that much chemistry. It's quite a lot of remembering. The main chemistry points that you're going to need to know is about the reactivity of alkenes, why they have low reactivity, and how to form cracking equations and isomerization and reforming equations. Okay, so I've got some questions for you to do. You'll probably need about 20 minutes to do it, so have a go, and then we'll go through the answers once you've finished. Okay, so we'll go through the answers. So, there isn't definitive answers for these, so if you've got something similar, fine. So draw the following alkanes as structural displayed in skeletal formula. Well, these do have definitive answers. This is my structural formula. This is the displayed formula showing every single bond between each atom in the molecule. And this is my skeletal formula, 1, 2, 3. If you're unsure about drawing these, have a look at the basic organic chemistry video. That should help explain them. 2-methylbutane should look like this. And 2,3,4-trimethylhexane should look like this for my structural. For my skeletal, which took a long time to draw, as you're all probably for my displayed, which took a long time to draw, as you're probably aware. And this is my skeletal. So we usually use skeletal because it takes 1/10 of the time to draw compared to structural or displayed. And also, when we come on to functional groups, I'll explain why we use skeletal as well. So, state and explain the difference in boiling points between the alkanes above. Okay, in general, it wasn't a very It wasn't a very well worded question. The idea was that as we increase the branch chain, the boiling points will decrease. So I've written that boiling point decreases as branches on the carbon chain increases because there is less points of contact, therefore a decrease in intermolecular forces, therefore requires less energy to overcome. Okay. Explain in terms of volatility how fractional distillation works. Again, if you've got most of these points, that's fine. There's no definitive way to answer this. But I've written that volatility is the ease at which a liquid turns to a gas, so I've defined it. Therefore, more volatile liquids move further up the column and condense at a lower temperature. These are smaller molecules with less intermolecular forces between the molecules. Large molecules are less volatile, therefore they have a higher boiling point, so condense further down the column. Okay. And lastly, icosahexane has 120 carbons in a straight chain that can be refined from crude oil. State the molecular formula of this alkane and draw the shape and state the bond angle around a carbon atom. So we'd use this general formula, so CnH2n plus 2, C120, H242. I know it's an alkane because it ends in ane. And then draw and state the bond angle around the carbon atom. Well, this would be my carbon atom. 2 hydrogens coming off, and this would be my carbon chain. Remember to do it 3D. I don't have to draw all of it because it will just be repeating. And this would be a bond angle of 109.5 degrees. Describe a process that could be used to make an icosahexane into a shorter hydrocarbon or into shorter hydrocarbons. Why would this be useful? Include an equation in your answer. Well, first I could crack it using a zeolite catalyst. So I've just made 5 moles of shorter alkane and 2 moles of an alkene. As long as you have an alkane it's shorter and an alkene, it doesn't matter which one you put down. Using either or both of the products produced in B, describe 3 different processes that could make them more useful. Include equations in your answer. So I've used isomerization with the PT catalyst. I've took my shorter alkane, my straight chain, and I've turned it into a branch chain. Okay, again, any example, as long as the molecular formulas are the same, that's fine. Reforming, I've used a platinum and aluminium oxide catalyst. And again, I've taken my straight chain alkane and I've put a benzene ring on it. And remember, this is the only thing which might be a problem. This would be C6H6. But here, we normally have a hydrogen, but we've had to remove this hydrogen to put this branch on. Therefore, rather than removing 4 moles of hydrogen, we'd have to remove 4.5 moles of hydrogen. Anything with the molecular formulas adding up, or the amount of products and reactants atoms on the same side equaling the same number, is fine. Okay, right, so I think that was a lot of remembering. So next lesson next lesson would be onto alkenes, which we'll be talking more about some chemistry. Okay, so go away, remember it, have a practice of it, and hope that was useful as always, and I will see you next time. Okay, bye bye.